Okay, so this question, as I said, it combines both thick and thin wall analysis. Okay, so let me verify what I've just said. Okay, so for point C or point B and point C, it uses thin wall analysis. Thin wall, hold on, wide flange analysis, not box beam. Why not box beam? Because it starts from two terminal. I'm drawing one terminal here. This is terminal 1. This is terminal what? 2. Right? Two terminals not related to one another is a wide flange analysis. Okay, but the shear stress at point A, right? Given the thickness is pretty wide, it's 120 millimeters, right? So this is a thick wall at point A. It is a thick wall analysis. Okay. All right. So interesting problem. So we know that the stress max is equal to that was given is 75 times 10 to the power 6 Pascal. Right. That's given, and this will be equal to Vy over Izz. Right. Qz max. Right. Divided by T. Okay, sorry. I wouldn't call it QZ max, but QZ at a certain point divided by T. Okay. Excuse me, I do apologize. Okay, so we have to identify where tau max is. We don't know. Now we don't know. Because it's affected by both QZ and T, right? For this case. Is it the centroid? We don't know. Okay, as I say, is it the centroid? Okay, so what do I mean by centroid? Is it the centroid over here? Okay, is it the centroid? Will be the tau max? We don't know. Okay, so this is the centroid. Right? So we have to find, is it point C, is it point B, or is it point A? So the first thing first, okay. Now you can appreciate why point C and point B is a what? Wide flange analysis, yes or no? Right? Because the terminal, they start from two separate terminals. That's the only reason. Okay. So let's find the shear stress at point C. All right, shear stress point C. So we know that it's a wide flange analysis. And we also know that the thickness is equal to 10 millimeters or 0.01 meter. Right? That's the thickness, right? Because in thin wall analysis, the thickness is perpendicular to the shear flow. Okay. So now we want to find the shear stress, not the shear, the first moment of area at point C. Okay. So we only need to consider this area over here that I'm shading. Okay. Right. So width, depth, y bar. Okay. So the width is 30. The depth is 10. The y bar is so 60, 160 divided by 2, right? Because it's top and bottom from the 160 minus 10 divided by 2. Okay. So this will work out to be 80 minus 5. Oh, sorry, 80 minus 5 times 10 times 30 is equal to 22.5 times 10 to the power 3 millimeter cube, or 22.5 times 10 to the power minus 6 meter cube. Okay, so that is at point C. So we can calculate the shear stress at point C is equal, not the shear stress, the ratio of QZ over T. Okay, so we have Vy over IZZ. QZ is 22.5 times 10 to the power minus 6 divided by the thickness, which is 0.01. Oh, hold on. Right. So the Vy, so 22.5 power minus 6 divided by 0.01 is equal to 0.5 power minus 6 divided by 0.01 is equal to 2.25 times 10 to the power minus 3 Vy over IZZ. So that is our shear stress at point. Then next we are going to find, all right, the shear stress at point B. Right, so shear stress at point B. So we are going to use again wide flange analysis. T thickness is now equal to 0.02 meters. Right, you can see Y is 0.02 meters, right? So this is the thickness now. So the area we're going to concern is the first moment of area we're going to take is also up to point C, and then we are going to consider this area also that I'm shading now, okay, up to here, right? So we're going to find Q at point B, right? So Q at point B, you have to be careful here, okay? This is where a lot of mistake can be made. Is equal to Q at point C plus, so the width is 20, the depth is 50. Yep, the depth is 50. Multiply by 160 divided by 2 minus by 50 divided by 2. Okay, so QC in millimeter cube is 22.5 times 10 to the power minus 3 plus by 22.5 times 10 to the power 3, not minus 3, sorry, plus 160 divided by 2 minus 25 divided by 2 times by 50 times by 20 is equal to 67.5 times 10 to the power 3. So 22.5 plus by 67.5. So it's 90 times 10 to the power. Wait, did I get this wrong? Hold on. 22.5, 20, 50. Let me do it again. 160 divided by 2 minus by 25 times 50 times 20 is 55. I don't know how I get 67.5. Okay, I'll do it again. 80 minus 25 times 50 times 20, 55 times 10 to the power 3. So 55 plus 22.5 is equal to 77.5 times 10 to the power 3 millimeter cube, or 77.5 times 10 to the power minus 6 meter cube. Okay, so now the shear stress at point B is equal to Vy over IZZ, right? And then the Q is 77.5 times 10 to the power 3 divided by the thickness is 20 millimeters, 0.02. So by looking at the ratio now, so 77.5 power 3 divided by 0.02 now is equal to 77.5 power minus 6. Sorry. Hey, I need to wake up, man. 77.5 power minus 6 divided by 0.02 is equal to 3.875. Right? Times 10 to power minus 3 Vy over Izz. Okay, I'll do it again, 77.5 power minus 6. Right. So what you realize that no doubt at point B, so this is where point B is, right? No doubt point B has is wider, right? But it has more higher first moment of area. That's why point B, the stresses, the shearing stress is higher than point C by looking at the ratio. Okay, so this is point C, right? And this is at point B, right? And because point B has a higher first moment of area compared to point C, but the thickness, right? So the thickness and first moment of area, they are both fighting, yes or no, right? And you see that this is no doubt this is wider, this is smaller, right? But because the first moment of area is much more bigger, so that's why point B has a much higher ratio of QZ over T. Okay. Excuse me. So next, we're going to find. Okay, I'm going to copy and paste so we can see the diagram better. All right. So next, we're going to find. Okay, find the shearing stress at point A, right? Using thick wall analysis. Now, again, the first moment of area is the tricky part. Now, before we go on, we now know that the thickness is equal to what? 0.12 meters. Okay, we know that now, right? We know that that is the thickness now. Okay, so from here, we have to, so the Q at point A is equal to what? Okay, let's draw this out. So you have to take the first moment of area of here, which we have, and also the first moment of area of here, which we have also. So this is where we say this is equal to twice the first moment of area of point B, right? Because just now the at point B is a wide flange analysis, we just use the right hand side. But because now it's a thick wall analysis, you have to consider the entire area above the centroid. Okay, where do I mean above the centroid? So this is above the centroid. All right, so this is our centroid. Okay, so the next one is plus the width is 120, right? The depth is 30. So you will ask me, Eugene, what are we doing now? Okay, so we are now doing this area down here. Okay, the one just said. Width is 120, depth is 30, multiplied by y bar is 30 divided by what? 2. So this will be twice of what? 77.5 times 10 to the power minus 6 plus by 30 times 15 times 120 is 54 times 10 to the power 3. Okay, I should use the 77.5 times 10 to the power 3 one, okay? Because now everything is millimeters. Okay, so 77.5 power 3 times 2 plus by 54 power 3 is equal to 209, okay, times 10 to the power 3. millimeter cube or